Hello, this video is about half-lives, so let's get right at it. Taking a look at what's on your equation sheet for AP here, they don't give you a whole lot for kinetics. They give you this one, which is our first order reaction. They give you this one, which is our second order reaction, and then this part, which we haven't talked about yet. But you can see it's t to the 1/2, which is also known as half-life. So here are the things you need to know about half-lives. Let's take a look at what a half-life even is. A half-life is defined as the amount of time required for 1/2 of a reactant to react. You've seen this before in nuclear when we're looking at like carbon having a beta decay into nitrogen, or rubidium doing a beta decay into strontium. In other words, how much time does it take for these to decay into different elements? That was the nuclear decay process. And I had this half-life, or this type of graph. In other words, we're looking at, if you've got 150, that's looking at pressure here, and you do half of it is now gone, that means you have 75. Your half-life went from here to here. And now if you want to do another half-life, you're looking at 75 going to 37.5, and your second half-life goes from here to here. You can see that these distances will be the same. That's how we've seen it before. And I'm going to say that AP is the same idea. So AP expects you to know, let's look back. I can able to connect a half-life of a reaction when it's a first order reaction. That's all they're looking at, first order reaction. And to justify that in use of, okay, we'll take that one part at a time. So I want to look at how the half-lives are the same each time. And that only happens if you have a first order reaction. Okay, at this point, I don't want you to write anything down. Just take a look. Here I've got a first order, and I've got that ln stuff. ln happens when you've got a first order reaction. Here I've got a second order reaction. That's that 1 over a stuff. I took those beginning equations, which are right up here, and I just kind of rearranged them a little bit, which is what you see here. And now what I'm going to do is do half-life. In other words, after one half-life, A over T, you have 1/2 of your original amount. These are the two values I'm replacing in there. So now A over T is going to go right in here. Boop. And AO, which is my original amount, goes right there. Then I'm doing some fancy math, just some algebra actually, to get to this equation. This is the equation that's on your AP sheet. In other words, this math is proving to you that after one half-life, in other words, when half of it has gone by, you will get this equation, 0.693 over K, every single time, which means the half-life is a constant value. Now let's look at something that's not a first order reaction. Here's our second order. I'm going to do the same thing. After one half-life, A over T, I have half of it left. I'm plugging that value right into here, doing some algebra again, and I get this value down here. Notice that the half-life is now dependent on how much you started with. And so it changes as you get less and less of an amount. So this is not constant. The name of the game is we have to know that when you have a first order reaction, the half-life is constant every single time. If you have something like a second order or zero order, that's not true. So we need to focus on that constant half-life each time. The good news is we just have to deal with a first order reaction. The student is able to connect half-life reaction to the rate law of a first order reaction. So in other words, you have to be able to plug in numbers here and solve for K or solve for half-life, depending on which they give you. I know you can do algebra. And justify the use of this relation in terms of the reaction being a first-order reaction. We're going to look at this part next. Justify means I can look at graphs and decide, can I use this equation or can I not? So this is two different labs, two different times. So this graph is the top one. They're both A over T. In other words, they're both a zero-order reaction. Or they're showing a zero-order graph. I can't say that it's zero order, I don't know yet. But they are showing the graph for it. A versus time, A versus time. And I'm trying to ask myself, which one can I actually use this equation for? In other words, which one is a first-order reaction? I don't have all the graphs with me, so I don't know for sure. If I had all the graphs, then I could see, oh, which one's linear and decide. But I don't have that here. I know you're looking at the bottom one saying, that's linear. I know, sneak peek. But let's take a look. So if I want to see the half-life of this top one, I'm going to start with maybe 0.1 right here, and go half of it, which is 0.05. This would be one half-life, right? Here to here, one half-life. Terrible line. 0.05, now I want to go to 0.25 is my second half-life. Here, I'm going to go kind of off the graph, to here. You see how this is a consistent half-life, but let's get 0.02. That's not the best because it doesn't go high enough. But these are constant times. In other words, the half-life, the t to the 1/2, sorry, is a constant value. If I look at this bottom graph down here, I'll start with that 0.1 again to 0.05. Here's 0.1, 0.05. This is your first half-life. 0.05 to 0.25, 0.025, sorry. Do you see how this distance right here, that's the amount of time for the first half-life, is totally different from this distance right here? I can clearly see that these are different. The half-life of this is not constant. This one right here, A over T, this is my 0 order. I can tell that. And I can also see it's not a first order because the half-life is not constant. My half-life is constant here, so this has to be a first order reaction. Only a first order reaction will have a constant half-life. Okay, so the name of the game for half-lives, what do you need to know? 1, what a half-life is. Boom. 2, first order creates a constant half-life. And 3, I know that even by looking at graphs. I can see the constant half-life, even if I've got a graph that doesn't show my first order or that ln graph being linear. If I take my graphs a little bit further, I snipped them out, you can see that this is my first order reaction, and it is a first order reaction. But I could also tell that using this part right here that the half-lives were constant.